The next thing that we're going to talk about is the displacement current, which I think is an absolutely remarkable thing. Okay, so let's first briefly review Ampere's law. So what was Ampere's law? Ampere's law says that suppose you have any distribution of current, and we'll just take a straight wire as an example. So any distribution of current will produce a magnetic field. If you surround this current distribution by any loop, and this loop was called an Amperian loop, and then you calculate the line integral of the magnetic field produced by the current distribution over the Amperian loop, line integral B dot dl over the Amperian loop, the result is going to be equal to mu0 times the current enclosed by the Amperian loop. Now, we have talked about this stuff before, but let's just quickly make sure that we are absolutely clear about what is meant by this quantity I enclosed. I enclosed means the current that's piercing the surface of the loop, right? So this loop has a surface. So you can think of I enclosed, the precise definition of I enclosed is that it's the current that's piercing this surface, right? And that's absolutely fine. However, you might remember that I had emphasized a certain subtlety here. The loop does not just have one surface. The loop could have an infinite number of surfaces. For example, I could draw a surface like this. So that surface also has the loop as its boundary, right? I could draw a surface like this. This also has the loop as its boundary, right? So all of these surfaces have the loop as its boundary. So when I say the current penetrating the surface bounded by the loop, it could be any of these surfaces, any of these infinite number of surfaces. And the math gives us the freedom to choose any surface we want, right? Though the flat surface is the easiest to think about and use when you're doing problems, but we are allowed to use any surface we want. So the precise definition of Ampere's law is that line integral B dot dl is equal to mu0 times I enclosed, where I enclosed is the current penetrating the surface bound by the Amperian loop, and you are allowed to use any surface you want. Okay, all right. Now, James Clerk Maxwell, who is the greatest hero in our entire subject of electricity and magnetism, noticed something very strange about this equation that we have over here, which we call Ampere's law. Maxwell noticed that this equation is not mathematically consistent. So I'm not going to get into the details of how what the precise problem with this was. But if you have a little bit of using a little bit of vector calculus, you can show that this equation is not mathematically consistent. So Maxwell noticed that in order to mathematically fix this equation, you have to add one more term to it. And so the fixed equation, the mathematically consistent form, looks like this. B dot dl is equal to mu0 I enclosed, and then you have to add another term, which is which for short it's written as mu0 id enclosed. So id is defined as the displacement current. This name was coined by Maxwell, and as it turns out, it's a terrible name, but now we are stuck with it. This is not a current at all. So I would not think of this as a current. It just has current in its name, and it has the same dimensions as current, but it's not a current at all, given the way we understand what a current is. What is the displacement current? The displacement current is this quantity. And this d is really a subscript, shouldn't be so large. the displacement current is this quantity. It's epsilon 0, which is our old friend from chapter 21. Epsilon 0 ddt of the electric flux. Where did the electric flux come from? Electric flux just means flux of the electric field. And where did electric fields come from? Whenever you have a current, the reason that the charges are moving through the wire is because there are electric fields in the wire, right? So those electric fields have a flux over the surface of the loop, and that is what the phi e stands for. It's the flux of the electric field over the surface of the loop, right? That is what displacement current stands for, right? And when you put this enclosed over here, id comma enclosed, it means that you're only considering the flux of the electric field over the surface of the loop, right? Because the electric fields can exist outside of the loop as well, but in principle, but you're only considering the flux of the electric field over the surface of the loop. So that is the term that you need to add in order to fix Maxwell's equation, in order to fix Ampere's law. All right, now let me demonstrate that Ampere's law can sometimes give you an answer that's very wrong. Okay, let us look at an example where Ampere's law fails. And I have a nice diagram on the PowerPoint slide, which I've copied over here. Okay, let us first focus on this diagram on the left. So what do we have here? So we have a capacitor which is being charged up by a battery. So there is a current flowing like this. Let's say that we want to find out what the magnetic field is at this point. And let us just assume that this stretch of wire is pretty long, right? I could probably make it a little longer. I want to find out what is the magnetic field somewhere over here, right? So using Ampere's law. So what I would do is I would draw an Amperian loop surrounding the wire, right? Okay, and then I could go through the same symmetry arguments. I could say that the magnetic field lines, if the stretch of wire where we are considering the magnetic field is pretty long, then the magnetic field lines would be concentric circles. That allows us to do the line integral, and so b times 2 pi r is what the line integral becomes. R would be this radius, and that is equal to mu 0 times I enclosed. Okay, what is I enclosed? If we consider the flat surface of the loop, then I enclosed is simply the current penetrating that flat surface. So that would just be the charging current I. So that would just be the charging current I, right? And so I enclosed would just be I. So I get b times 2 pi r is equal to mu 0 I. And so b is equal to mu 0 I divided by 2 pi r. And that is exactly the correct answer, because that's what we would get from experiments. Okay, now suppose I do the following. I say that I just want to be difficult. So I say that I don't want to work with the flat surface of the loop. Why don't I choose a wonky surface? And the surface that I'm choosing is the one on the right. So this surface. This surface mathematically is perfectly acceptable because it just has the loop as its boundary. So there's nothing wrong with this surface at all. We just made a huge deal about how you can choose any surface you want, right? So what's wrong with choosing this surface right here? The problem is, what is the current penetrating this rounded surface? There is no current penetrating the rounded surface at all, right? Because the current stops, there is no current flowing through the in between the plates of the capacitor, as you know. Charges cannot flow through the dielectric, right? So there is nowhere on this surface that a current is going through, is penetrating, right? So this surface is not touched, not being penetrated by a current at all. As a result of that, the right hand side of Ampere's law just becomes 0. So if you use the rounded surface, so this was for the flat surface. For the rounded surface, B times 2 pi r, the left side of Ampere's law will remain the same, for the same Amperian loop. I enclosed is 0. So that means B is 0. So if you use the rounded surface, you're getting the wrong answer, right? If you actually do an experiment and measure the magnetic field, you'll see that it agrees with mu 0 I divided by 2 pi r. So that is the correct answer. But using the rounded surface, you get the wrong answer. Now you might say that why should I use the rounded surface? Why should I care? You should care because mathematically it's allowed. So you have 100, nobody can take away your freedom to use any surface you want, right? So it's surprising that the rounded surface here gives you the wrong answer. That points to the fact that there's something wrong with Ampere's law. Let us see how this situation would be resolved if you included the extra term. So I'm going to draw the diagram here again. These are the capacitor plates. This was our Amperian loop. And this is the weird surface. I'll just assume that this part of the surface that's in between the capacitor plates is parallel to the plates. That assumption is not necessary. It just makes our calculation a little bit easier. But it's absolutely not. It doesn't take away any of the generality here at all. It just makes it makes it easier to calculate. So, okay. The full form of Ampere's law is B times 2 pi r is equal to mu 0 I enclosed plus, according to Maxwell, it's mu 0 times ID enclosed. So if we plug in the form of ID, it's mu 0 times epsilon 0 d phi e dt, right? Okay. We've already seen that if you use the curved surface, then I enclosed is 0. So that was the problem earlier, right? Let's see what this second term gives us over here. Right? So for the second term, we need to calculate the flux of the electric field over the Amperian loop, or over the surface bounding the Amperian loop. Now, the electric field lines are only present in between the capacitor plates. There's no electric field outside the capacitor plates. Of course, we are considering an ideal capacitor here. So the electric field lines are only present between the plates of the capacitor, right? And for simplicity, we've assumed that the part of this weird surface that's in between the capacitor plates is parallel to the plates. So that just makes it easier for us to calculate the flux of the electric field. So we needed to calculate the flux of the electric field over this whole surface, but we just need to do it for the part of the surface that's in between the plates, because that's the only place where there is an electric field. And the area of the surface that's feeling the electric field has the same area as the plates, right? So calculating the flux is very easy. So we just need to know what the electric field is. Let's say that the charge on each capacitor plate is Q. I mean plus Q and minus Q. Okay. So the electric field is going to be sigma over epsilon 0, as you know. So that's Q divided by A over epsilon 0, right? All right. So the flux of the electric field is going to be E multiplied by A, right? So it's E times A times cosine of the angle between E and A. So the normal to the area can be taken to be in the same direction as the electric field. So E dot A just becomes E times A. All right. So we can plug in what we know for E. So E times A is just Q divided by epsilon 0, right? Now, if we take d phi E dt, we get dq dt. So my phi's are beginning to look like q's, so let me just fix that. I've used too many colors, okay. All right, so d phi E dt is just dq dt over epsilon 0, right? And then we can do, so that's, we found the d phi E dt. Then we can plug this d phi E dt right in over here, and let's see what that gives us. B times 2 pi r is equal to mu 0 times epsilon 0 times 1 over epsilon 0 dq dt. The epsilon 0 cancels out. Now let's think for a moment of what dq dt means. dq dt is simply the rate at which charge is being transferred to the capacitor plate. So it's the rate at which charge is being, the rate at which the positive plate is gaining charge and the negative plate is losing charge, right? So that's what dq dt is. So we just need, so dq dt is nothing but the current, right? So we get B times 2 pi r is equal to mu 0 times the charging current, right? And so we got the correct answer when we included the extra term that Maxwell suggested. So the extra term came to our rescue and gave us the correct answer for this weird surface, right? I mean, so B would be, from here would be mu 0 I divided by 2 pi r, which is the correct answer. And we would not have gotten it if we had not included that extra term from Maxwell's equation. So this extra term is the displacement current, right? And together with this term, Maxwell's equation, this equation of Ampere's law is called the Ampere-Maxwell law. Okay. Now, does this extra term tell us anything interesting that we didn't know? Absolutely. It tells us that you can have okay, does this extra term tell us anything that we didn't know? Does this have any interesting physical significances? Absolutely. Let us consider this question on the next slide. Is there a magnetic field between the plates of a capacitor? Now, at first, this might seem like a really silly question. Like a capacitor, what does that have to do with magnetism? Where would a magnetic field come from? The answer is, if you look at this new term, if you look at this equation, and if you look at this term over here, you can see that you have a derivative of the flux of the electric field, right? So if the electric field is fluctuating, you could get a magnetic field. So what this is telling us is the amazing fact that a fluctuating electric field can create a magnetic field. Recall that earlier in this chapter, we saw the amazing fact that a fluctuating magnetic field can create an electric field. And now we are seeing that a fluctuating electric field can create a magnetic field. So d phi E dt measures the rate of change of the electric flux. And on the left side, you've got a magnetic field. So this equation is telling us that a fluctuating electric field can produce a magnetic field, right? So this is the amazing symmetry of nature. A fluctuating magnetic field can produce an electric field, and a fluctuating electric field can produce a magnetic field, right? So what's an example of that? Well, suppose you have a region where you have an electric field uh, that is increasing or decreasing, right? Suppose you have this region, this circular region where an electric field is getting stronger, then you will have magnetic field lines, which are concentric circles because of the circular symmetry. And so these magnetic fields will be produced because the electric field is fluctuating. So if you have a capacitor which is being charged by a current that's increasing, then as the current is increasing, the charge on the capacitor plates is increasing, the electric field between the capacitor plates will keep getting stronger, and so that changing electric field will produce a magnetic field in between the plates of the capacitor. And you can measure, if you put a little compass in between the plates of the capacitor, you'll see that there is a magnetic field. Okay. And this magnetic field is produced strictly by the fluctuating electric fields. All right. Let us do an example of a problem on this. A circular, okay, so this is the problem on slide 32. Let us take a look at the problem. A circular parallel plate capacitor with plate radius R is being charged with a current I. Calculate the magnitude of the magnetic field at a radius R from the common axis of the plates. All right, and the answer is given here. So let's see if we can figure out the answer ourselves. So you have a capacitor, a parallel plate capacitor. The plates are circular. So let me just draw it like this. So this is our parallel plate capacitor, and with two circular plates. The radius of the circular plates is R. All right. You want to find out the magnetic field at a radius little r from the common axis of the plates. So you want to find the magnetic field somewhere at this point in between the plates. The radius of the plates is capital R. All right. So hopefully it's clear to you why there would be a magnetic field. At first it would be very, very surprising because we talked about capacitors when we were buried in electric fields. We were very far from talking about magnetic fields. So you might think, where does a magnetic field come from? But just to reiterate, you have a magnetic field at this point. Let's call this the point P. You have a magnetic field at the point P in between the plates of the capacitor because the capacitor is being charged up. And so the electric field between the plates of the capacitor is increasing. Whenever you have a fluctuating electric field, that produces a magnetic field. Now, what would the magnetic field lines look like? So this is a situation which has circular symmetry, and in this elementary course, we only look at circular symmetry for these things. So when you have circular symmetry, the magnetic field lines will form concentric circles, right? So the magnetic field lines would be concentric circles in this region. All right. So hopefully it's clear to you why there is a magnetic field. Now we are going to apply the ampere Maxwell equation to calculate the magnetic field, right? Okay, so we are going to proceed the same way in which we proceeded when we used Ampere's law to calculate magnetic field. We are just going to be using the full form of Ampere's law, which is the Ampere-Maxwell law. So how do we use Ampere's law? We just draw an Amperian loop which is in accordance with the symmetry of the problem, which passes through the point in question, right? So clearly the Amperian loop that we need to draw is a concentric circle like this, another concentric circle. Okay, let me see if I can make this circle a little bit better. It's not that much better anyway. So our Amperian loop is another concentric circle. I'll draw the common axis. Maybe that'll improve the diagram. No, it doesn't. Anyway, all right. So, okay. And now let's apply Ampere's law. I mean the full Ampere Maxwell equation to this Amperian loop. Right? So, Ampere Maxwell equation is B dot dl line integral. I'll just write the whole thing. Line integral B dot dl is equal to mu 0 I enclosed plus mu 0 epsilon 0 d phi e dt. Right? Okay. Is there any current passing through this the surface? We are just going to work with the flat surface now. Is there any current penetrating the flat surface of the red loop? The answer is no. So there is no I enclosed, right? So the only contribution again comes from the second term in the Ampere-Maxwell equation. So we have to calculate the second term, right? So we are just working with the flat surface of the loop. So we just need to find the flux of the electric field over the flat surface of our Amperian loop, right? Now, the flat surface of the loop is parallel to the plates. So finding the flux of the electric field is very easy. So if the electric field is E, phi E, the flux of the electric field is going to be E multiplied by the area of the loop, which is pi r square, right? What is E? E is just going to be sigma divided by epsilon 0. So it's sigma divided by epsilon 0 pi r square. And so that is going to be Q divided by A epsilon 0 pi r square. That is our phi E. What is d phi E dt? That is going to be dq dt 1 over A epsilon 0 dq dt pi r square, right? And what is dq dt? dq dt is the rate at which the charge on the plate is changing, and that is exactly equal to the charging current. So it's just going to be I divided by A epsilon 0 pi r square is d phi E dt. All right, we can now plug this back in to the Ampere-Maxwell equation. So B dot dl, line integral B dot dl, which is just going to be B times 2 pi r, we might as well just write that down, is equal to mu 0 times epsilon 0 times d phi E dt. So mu 0 times epsilon 0 times the d phi E dt that we just found. So I divided by A epsilon 0 pi r square, epsilon 0 cancels out. So you get B times 2 pi r is equal to mu 0 times I divided by pi capital R square times pi little r square. The pi cancels out as well. And so you can just solve for the magnetic field. So B is equal to mu 0 I divided by 2 pi r square times little r, and that is the answer. All right. Okay. So we can now put together everything that we have learned in electricity and magnetism. And as you can see now, it all boils down to 4 equations. So these 4 little equations are called the Maxwell equations. And amazingly, they encapsulate everything that we know about electricity and magnetism. So the first equation is Gauss's law for electricity, which says that the surface integral of the electric field over a Gaussian surface. So if the surface integral is taken over a closed surface, there is a mathematical convention that you just put a circle around your 2 integration signs to indicate that it's been taken over a closed surface, right? We have normally written this as surface integral and then put a little and written Gaussian surface underneath. But now I'm just using the formal mathematical notation. So E dot dA or ds, I've forgotten which I've been using, I think I've been doing E dot dA. I'll just follow what's on the slide. So E dot ds is equal to Q enclosed divided by epsilon 0. So this is Gauss's law for electricity. Surface integral of the magnetic field over a closed surface is equal to 0. So why would the surface integral of the magnetic field over a closed surface be equal to 0? That is because the magnetic field lines always form closed loops, right? So let me just quickly talk about this point. I don't remember if I've discussed this in class, but it's an important point. So let me just go over that. The magnetic field lines always form closed loops, right? So these red circles are all magnetic field lines. So they always form closed loops. So if you have a surface, let me draw a surface like this. If you have a closed surface, remember that these red circles are actual loops, whereas the black circle, black shape represents a closed surface. The number of field lines cutting the surface one way has to equal the number of field lines cutting the surface the other way, because the field lines form closed loops. So if you consider this field line coming in over here, you can see that this field line is going out over here. This field line coming in over here is going out over here. This field line coming in over here is going out over here. So every field line that enters the closed surface has to exit the closed surface, because the field lines form a closed loop. It's not possible for a field line to come in and terminate over here. That would be possible if you had magnetic monopoles, which are the analog of uh, electric charges, just like you have a positive charge or a negative charge. If you did have magnetic monopoles, which are like an isolated north pole or an isolated south pole, then that might have been possible. Then, just like the positive charge, which acts like a source of field lines, a north pole, a magnetic monopole, a monopole would give out magnetic field lines, and a south monopole would act like a sink for magnetic field lines. But we don't have anything like that, and so magnetic field lines always form closed loops. And so that is why you cannot have a field line coming in and not going out. You can, of course, have field lines which are entirely inside. They don't cut the surface at all. So you can see that now think back to what the flux means. Flux means that flux counts the number of field lines which are cutting a surface, right? So if the field lines happen to form closed loops, the flux has to be 0, because the number of field lines cutting the surface one way have to equal the number of field lines cutting the surface the other way. So hopefully it's clear to you that since magnetic field lines always form closed loops, the flux of the magnetic field over a closed surface is equal to 0. So this is very, very important, and I'll just write this down. The significance of this is there are no I'll write this one first. Field lines, magnetic field lines always form closed loops. And this is because of the experimental fact that there are no magnetic monopoles. So this is what Gauss's law, so this second equation is called Gauss's law for magnetism. The fact that the right hand side is equal to 0 signifies these two facts. I mean, these two are just pretty much the same thing. So it basically tells you that there are no magnetic monopoles. Now, there is something very strange about this. We have no idea why magnetic monopoles don't exist. There is really no reason why they should not exist. In fact, they are not forbidden by any of the processes that predict that describe how matter came into existence and stuff like that. there is nothing there that forbids the creation of magnetic monopoles. So it's a big surprise that they don't exist. In fact, about 10, 20 years ago, there was a tremendous interest in searching for magnetic monopoles, and many different ways were techniques were thought up in order to try to detect magnetic monopoles. Uh, there are no magnetic monopoles on Earth. There also don't seem to be any magnetic monopoles uh, in the galaxy, uh, or in space anywhere. So it just seems that magnetic monopoles just don't exist anywhere, and it's a very strange mystery why they don't exist. Okay, it's just an experimental fact that they don't exist. Now, I could go on talking about this, but you don't want to listen to this video all day today. But uh, there is there was a very famous scientist named Dirac. If you major in physics, you're going to hear about Dirac a lot. So Dirac, one of the amazing things that Dirac showed, and this is like one of his tiniest accomplishments. He's done much more important things than this. He showed that even if there is one magnetic monopole in the universe, just one, that would beautifully that would give us a beautiful explanation why charge is conserved. So another thing that we don't understand is why charge is conserved. Right? There's no good explanation for that. Um, Sorry, why charge is quantized, not conserved. So we don't have a good explanation for why charge is quantized. Uh, but if there was one magnetic monopole in existence, it would explain, it would give us a beautiful explanation for that. Um, so anyway, so it's a mystery why magnetic monopoles don't exist. So that's our second equation, right? The third equation that we learned in this chapter is this one: line integral E dot dl is equal to minus d phi b dt. And I'm writing, since we have two kinds of flux, magnetic flux and electric flux, I'm going to write phi b for magnetic flux and phi e for electric flux, just to distinguish between them. So this equation we've talked about in a lot of detail in this chapter. This equation is telling us that when you have a fluctuating magnetic field, it can produce an electric field, right? Okay, and the last equation is tells us that line integral b dot dl, that's the one that we just learned, is mu 0 I enclosed plus mu 0 epsilon 0 d phi e dt. So this equation, I'll just number these equations so they're easier to, this is 1, this is 2, this is 3, and this is 4. So equation 3 tells us that a fluctuating magnetic field creates an electric field, and equation 4 tells us that a fluctuating electric field can produce a magnetic field. These four magnificent equations summarize all the knowledge there is regarding the subjects of electricity and magnetism. So the entire subject of electromagnetism is summarized by these four simple and beautiful equations. So this is very, very amazing and very beautiful, I think. So Maxwell put these equations together. So I just wanted to point out, emphasize one thing. The Ampere-Maxwell equation, Maxwell added this extra term, and he did this purely mathematically. He didn't do any experiments or anything to figure out that an extra term has to be there. He just added that term purely on mathematical reasoning. And amazingly, it tells us something about the world that we didn't know, that a fluctuating electric field can create a magnetic field. So that's an amazing thing, where the mathematics tells you something that you didn't know about the world. You learn something mathematically before actually seeing it in the real world. There is another amazing surprise hidden in these equations, which we will see later on. So I don't want to spoil the surprise now. We are going to see that in two more chapters, that there's an amazing gem hidden inside these equations. All right, so I'll stop the lecture here.